Alright, this is 3.4, zeros of polynomial functions. We're going to pull everything together today, so this is going to be probably the toughest section, and it might take us a few days to get through, but it'll hopefully do all these problems and maybe try them without the video a second time. We'll get through it and we'll learn something from this. So first problem is wants us to use synthetic division to prove that negative 10 is the root of this. So negative 10, this is the coefficients would be 1, negative 7, negative 100, 700. Make sure that you're not missing an x, x cubed, x squared, x to the first, x to the 0th. So all of our coefficients are there. All right. Now we drop down the 1 and we multiply, we add, we multiply, we add, we multiply, and that's a good sign. We get no remainder. That means that was a root. It means negative 10 was the root of the equation. So what that means then is that x cubed function is now x plus 10. That's the factor if the root is negative 10. And then this factor, which is a quadratic, x squared minus 17x plus 70. So this cubic factors into this linear factor in this quadratic. Now I'm going to factor this quadratic or use the quadratic formula to get the other zeros. They said use the result to factor the polynomial completely, so it should actually factor. So let's see if we can factor this. X minus 7 and x minus 10, they multiply to be positive 70 and add to be negative 17. So there's our polynomial. And let's double check if they wanted us to write it a special way. Nope. We can just write it just like this, and that should work. Okay, the next problem is a similar problem. It's a cubic. We're going to factor it, but this time this quadratic that we get is not going to be able to be factored, and that's called an irreducible quadratic. That means that basically this cubic looks something like this, where it's got one real zero, but the other two are imaginary. The other two zeros that would come from this quadratic, for example, are imaginary. So we'd have to use the quadratic formula in order to get them, and they would be complex numbers. So let's just use synthetic division to get this quadratic. First thing we need to do is find a linear factor from this. We need to find a real zero of this cubic polynomial. So we're going to graph this thing on Desmos, and when we graph it, or in your calculator, negative 4 is a real zero. The other two are imaginary, like we said, because that's the irreducible quadratic. So negative 4 is a 0. That means one of the factors is x plus 4. And then there's an irreducible quadratic left over. In order to find it, we're going to divide the 0 into the polynomial synthetically. 1, 7, 16, 16. Now we should get no remainder, we know, because this factor goes into it. So 1, negative 4, we add, we get 3. This would be negative 12. Drop this down, we get positive 4. Multiply, we get negative 16, no remainder. So this quadratic is x squared plus 3x plus 4, where a is 1, b is 3, and c is 4. All right, the next problem gives us a fourth degree polynomial. So we know it has 4 zeros. This one says 2 are real, 1 and 7, and the other 2 are irrational. Well, so all 4 of them are real, 2 of them are whole numbers, and the other are irrational numbers. So let's take the 2 and divide them in. Now, the factors are x minus 1 and x minus 7. So if we wanted to, we could FOIL this out and get x squared minus 8x plus 7, and we could divide it in using long division into this polynomial. That would work just as well to get what's left over. In fact, that might even be quicker if you like long division. But a lot of you guys are used to synthetic, so we'll use synthetic to divide 1 into this polynomial, and then we'll divide 7 into what's remaining. So when you divide 1 in, you get 1, negative 4, negative 24, 20, and 7. And make sure you're not missing an x value, so we got all the coefficients there. So we drop this down, we get 1, multiply, we get 1, add, we get negative 3, multiply, we get negative 3, add, we get negative 27, multiply, negative 27, add, you get negative 7, multiply, negative 7, and no remainder. So we have left over this cubic now that we've divided this linear factor in. So let's divide the other one in, which is 7, into this polynomial. So same thing, we drop down the 1, multiply, gives you 7, add, gives you positive 4, multiply 28, add 1, multiply 7, and no remainder. So what's left over as the irreducible quadratic then is this polynomial x squared plus 4x plus 2, which is a quadratic. We know these are irrational zeros that come from this, So we know they're not going to be whole numbers, so we're not going to be able to factor it then. We'll have to get this from the quadratic formula. Opposite of b plus or minus the square root of b squared minus 4ac all over 2a. This is 16 minus 8, so this would be 8 inside of here. And this is 2. All right, we can change that into negative 4 plus or minus. I'll change 8 into 4 times 2, and then take the square root of 4 as 2. So this would be 2 square root of 2 all over 2. Now 2 goes into 2 once, and it goes into 4 twice. So it's negative 2 plus or minus the square root of 2. Those are our other two irrational answers. Negative 2 minus the square root of 2 is the smaller one, and then negative 2 plus the square root of 2 is our bigger one. Okay, the next question gives us a fourth degree polynomial, wants us to find all the zeros. We can obviously graph this in decimals. Let's try to do it without once. Let's see. It looks like it factors, so let's write two quadratic factors, and then two things that multiply to be negative 15 had to be negative 23. So let's try negative 25 and positive 2. That works to factor this thing. Now this factor factors into x minus 5, x plus 5, because it's a difference of two squares. And this one is an irreducible quadratic. I know that because it's a polynomial, it's a quadratic that shifts it up 2 units, so it doesn't have any real zeros. It has two imaginary ones. This says find all the zeros, so it wants us to enter our complex numbers in as a plus bi. So obviously we have 5 and we have negative 5. But we also have two complex zeros that come from this. To find those, I'm going to set that equal to 0 or use the quadratic formula. I think it's easier to set it equal to 0, subtract 2 from both sides, and then square root. So we get x equals plus or minus I square root of 2. So we would say I square root of 2 comma negative I square root of 2. All right, next problem wants us to find a degree 3 polynomial whose coefficient on the leading term is 1. So we know the zeros are x plus 5. I'm sorry, the factors are x plus 5 because the 0 is minus 5. And also x minus 5i and x plus 5i because those are the complex zeros. So let's multiply this out first. When we do that, we get x squared. The middle terms are going to cancel. The last term is going to be negative 25i squared, but I squared is negative 1. So this turns into x squared plus 25 from this factor. We still need to multiply that by x plus 5. When we do, we get x cubed plus 25x squared plus 5x squared plus 125. So there's our cubic polynomial. We'll write it by adding these two terms together. Simplify, plus 30x squared plus 125. That's the answer we're looking for with our leading coefficient 1. So that will work. Okay, this is a similar problem where it gives us two of the zeros right here, and then it tells us what the factors would be then as well, x minus those complex zeros. So it wants a quadratic, which is what we get if we FOIL this out. So when we FOIL it out, we get x times x, which is x. We get x times negative, so it'd be negative x times 2 plus I. And then when we do the next term, so it'd be negative, x times quantity 2 minus I, if we FOIL second times first. And then last times last, double negatives cancel, and we end up with 2 minus I times 2 plus I. Okay, so I can distribute this negative x as well. That gives me x plus negative 2x plus xi, or I'm sorry, minus xi. And then this gives me plus negative 2x, positive xi. And over here, I get 4, middle terms cancel, and the last is negative I squared. I squared is negative 1, so we have 4 plus 1, which is 5. And then we have these terms cancel. It's in a different color, 5. These terms cancel, and then I have negative 2x to make negative 4x. And I also have, I'm sorry, this should have been x squared right there. First term, x times x is x squared. So I got those, and I've got the x squared, so that's my quadratic right there. So it wants x squared minus 4 plus 5. This problem's a little tougher. It gives us one of the zeros. If one of the zeros is 3 minus 2i, then we know that the factor is x minus that 0. But we also have another 0 if with complex conjugates are both zeros. So 3 plus 2i is another 0. They always come in conjugate pairs. Complex zeros do. So if 3 minus 2i is a 0, so is 3 plus 2i. So we know that two of the factors then are these. Let's multiply this out and we can get that irreducible quadratic. And then we can divide it in with long division into this fourth degree polynomial. Okay? I mean, obviously, we could graph this and get those real zeros as long as they're whole numbers anyway, from a graph. But let's do it algebraically because we need to show our work. All right, so let's multiply this out. We get x squared minus x times 3 plus 2i minus x times 3 minus 2i. And then plus 3 minus 2i times 3 plus 2i. And like the last problem, at least with x squared, we know we're going to have negative 6x here. If you follow the pattern from the last one, the same thing happens. These xi terms always cancel, always. So we always end up getting whatever this is times 2. And you can FOIL this out to see that. But same thing here, you know. So over here we get 3 times 3, which is 9. And then the middle terms cancel, and the last terms are minus 4i squared. So I squared is negative 1, so it's 9 plus 4, which is 13. So here's my quadratic right here that you'll get if you FOIL this all out and simplify. Now I need to divide it into this other polynomial, x to the 4th minus 9x cubed plus 30x squared minus 33x minus 13. So I need to put something up here to multiply by x squared to get x to the 4th. That'd be x squared. X squared times x squared is x to the 4th. Follow through. It'd be negative 6x cubed plus 13x squared. All right, subtract. And let's see. You get negative 9 minus negative 6 would be negative 3x cubed. And then 30 minus 13 is 17 x squared. So now we drop down the next term, which is minus 33x. And we start over. So now what do I multiply by x squared to get negative 3x cubed? That'd be negative 3x. Follow through. So negative 3x times negative 6x is positive 18x squared. And then 13 times 3 is 39, so it'll be negative 39x. Now subtract, and this gives you 17 minus 18 will be negative x squared, and then this will be plus 6x. And then I'm going to drop down the negative 13. So what do I put up here to multiply by x squared? To get negative x squared, that'll be negative 1. I'll do this with different color. So negative 1 times x squared gives me negative x squared. Negative 1 times negative 6 gives me positive 6x. And negative 1 times 13 gives me negative 13, which is good because I don't want a remainder in this problem. So 0 remainder when you subtract. So that's left over. So I can write out what the polynomial is now. I know it's this factor, which is what I got when I FOILed up the two complex zeros, x squared minus 6x plus 13, times this other quadratic that I got when I divided the polynomial. So that would be x squared minus 3x minus 1. So there is the fourth degree polynomial factored into two quadratics. Now, I want to look at this one because I already have the two zeros in this one. They're complex. They were given to me. But this one, there's two irrational zeros that come from here. I'm going to have to find them with quadratic formula. So that'd be opposite of b, plus or minus the square root of b squared minus 4ac all over 2a. So double negatives go positive. 9 plus 4 is 13. So my answers are 3 plus the square root of 13 over 2, and then also 3 minus the square root of 13 over 2. And you might want to do the 2 into both of these like this. Might be easier to enter in that way. But those must be the two zeros that they're looking for. And they want the smaller one first. Obviously the smaller one's when we subtract. So there's the smaller, and there's the larger.